Okay, so we're going to start talking about PCB layout. And PCB layout is like the most challenging, but also, in my opinion, the most fun part of PCB design. This is where you're going to actually put things on the board, connect them with wires, and design the whole actual physical board that you will manufacture in the end. So there's a lot to this. We're going to go over just the basics of it and how to do it in Altium and some tips and tricks. But you could spend hundreds of hours going over all the like physics and information and things that you need to do really great PCB layout. But we'll just do an intro. So start out with some terminology, along with some examples. So a trace or a track is like the copper path that connects pins. So here you see like this is a component and this is a component, and you're connecting them with a trace. So that's going to be, when you manufacture this is going to be translated into into copper on the board. A via is a plated through hole between layers that takes a trace to the opposite side. So let's say you want to switch from the top layer to the bottom layer. You place a via, it punches a hole through the board and connects the bottom to the top in that place that you've selected. It's just a way of switching layers. And a pad is a piece of copper for soldering components. So like the pad of a component. So this component has two pads, VDD and ground. This is a capacitor. So yeah, it has two pads, and these will be, again, exposed copper that you solder a component to. So those are just some terminology reviews. Make sure you understand this. So the first thing you do when you go to PCB, and we'll go over this in the video example, but you're first going to import all of your components, and it's going to just show up like this. You're just going to see a big mess of components connected by this little rat's nest here of connections, and that's showing you like what's connected to what. So this pin is connected to this component, and there's a line between them. The first thing you're going to do is just do some like rough placement of where your components go. So your microcontroller, any like ICs you have, big components. Generally, if you have something, so the badge we're designing, the clock tower is not something that's being mounted anymore. It's not actually like a functional thing. It's just basically a toy. But if you have an actual PCB, usually you're going to have mounting holes in the four corners, so that it can be mounted to some chassis or thing that or like stand for your testing. So generally, like for your final product, for instance, you're gonna want to place mounting holes in the four corners. Place them out like, don't place them 36.28 millimeters apart, because then you're doing mechanical design to mount this thing. It's gonna be kind of a pain in the ass. So just place them like 50 millimeters apart, or something that makes sense. So either you or the mechanical engineer who's designing this chassis is not like banging their head against a wall. Headers. So if you have anything that's like plugging into this board, again, not really a huge thing on this board, but if you have anything that's like plugging in externally, you're going to want to place those around the edges so that they're easily accessible for a human to interact with. We talked a lot about decoupling capacitors. You're going to want to place those close to the pins that they are decoupling. So if you have, a VCC pin here and a VCC pin here, for instance, you want to place a capacitor here, place a capacitor here. If you place like two of them over here, it's not doing anything for over here. The point is that like any local signal BS that's going to be going into this pin is filtered directly before it goes to the pin. Otherwise, it's not doing its job. So just put the capacitor close to the pin that you are decoupling. The last thing you'll probably place is your like just resistors and capacitors, like pull-ups. Those don't really matter where you place them too much, and other things like that that are less critical to your signal paths. You'll place last. You can define the dimensions of your board. I'll show you guys how to like define an outline of your board. You can have some nice rounded edge corners if you want. In this case, you'll draw a little clock tower. If you want, I guess you could do whatever you wanted. You don't have to draw a clock tower, but that's what this board is. And then again, make it something logical. Don't make it 48.6 millimeters by 59.87 millimeters. That's just obnoxious. Don't do that. Just make it some like logical dimensions. Again, for this badge, it does not matter because it's not being mounted anywhere. These are just things that when you do your final project, or you're ever doing PCB design for industry, or for a group that you're working with, that just do things logically. You'll thank yourself later. These rounded edges are really nice because if you put like you'll see you have a 3 millimeter like radius here, and then you can put like your M3 mounting holes here, and they line up quite nicely. Everyone's happy. They're not pointy. And yeah, you'll define the board outline on a mechanical layer. We're going over layers a little bit, but we'll talk about it more. That just should be its own layer of just the board outline and probably like mounting holes. Okay, so yeah, now we're going to talk about layers a little more. So the top and the bottom layers are component placement and routing layers. You can also have internal signal layers. So if you want like a 4-layer board or a 6-layer board or a 16-layer board, you'll have internal layers. But for now, we'll be working with 2-layer boards that just have a top and bottom. Maybe if you're a final project, if you're doing something kind of intense, you might need internal ground and power layers. But for now, let's just talk about 2-layer boards, top and bottom. That's what this copper that's pointing to here. It's like where everything is like etched in, the actual like metal that connects things and connects components, etc. Your solder mask is a protective layer coating the PCB, so that's this green layer here. And what that is like, if you've ever seen like, if you've ever seen a PCB, they have a color, right? Like Arduino Unos are blue, and most, kind of hobbyist PCBs are green. That's the solder mask. It's basically covering up all of the copper, like protecting everything, so that if you don't like short something, and it protects it against like the elements, and it's just like a protective layer basically, and it covers the whole board, and that's that color. So that all the copper is not exposed. You have your mechanical layers. So there's a bunch of different mechanical layers. You've seen these when you made your components in Altium. You saw like the 3D body layer, your board outline, a courtyard of like, keeping space around component. Those are all mechanical layers. The silkscreen is this top layer here. It's just like the text and any images you have on a board. So if you've seen the clock tower boards I gave you, those have like little things that say like R1, R2, R3. That's on the silkscreen. That's just like text. It's just, it's basically just like printed on there. And that will give you information about the board and any like component placement things and all that kind of stuff. So that's the silkscreen. So that means. And solder paste is where paste will be applied to connect components. So if you have like exposed pads for components, if you're getting your board assembled by a manufacturer and not by like by hand by yourself, they'll put solder paste over all the components, all like the exposed copper that needs components to go on it, and that will just help solder them when they go through the assembly process. We'll talk about that more when we talk about manufacturing. Okay, so routing. Routing refers to like connecting things together. So the traces that you draw are like your routing essentially. All of the pins in one net and deconnect to each other. So if you have ground in 3 different places, or let's say you've ground in 4 different places, you can't connect 2 of the grounds and then connect the other 2 grounds. You need to connect all of the grounds together. Otherwise, it's not ground. It's like ground 1 and ground 2. They all need to be connected to each other. Same thing with power, same thing with any other pin. They all need to be connected to each other. The software will show you what must be routed. So I showed you earlier this little like nest here. These are just showing you the connections that need to be made. Not necessarily like in the order that you should do them. Like just because you see this connects here to here does not mean that's how you should connect them. Maybe there's a whole other loop that's a better way, but that will show you like just generally what needs to be connected. You can route on the top layer, the bottom layer, and the internal layers. So here, red is top and blue is bottom. You'll get very familiar with that. These are different layers. So you can see the crossover here. That's okay because they're on different layers. This is the bottom and this is the top. So those can cross over because they're on different layers. And same thing if you have internal layers, you can route on those. If you have internal power ground layers, internal metal layers, you can route on those as well. If you want to switch layers, so let's say like you want to get from here to here, but you can't draw over this because then it would short all these connections. It's not going to let you draw over this. It's not going to let you trace over here. So what you can do is you can switch layers. So if you're routing all on the bottom layer, and then you could just switch to the top layer with a via. So it's again just a plated through hole that goes through the top. You go up to the top, go over the other traces, then you go back down to continue routing. It would generally suggest trying to route, bottom in one direction and then top in like a horizontal direction when there's things like overlapping. Because like I just mentioned, let's say this was a a top layer and this is a bottom layer. How are you going to get across this if you don't have any internal layers? You can't cross another trace. So you'd have to do like a lot of weaving and bobbing around with vias, and it would be less ideal. You really want to minimize the amount of vias that a trace goes through to maintain signal integrity. It's okay to use them, and again, for all these layers we have here, for all the components we have here, it's really like low frequency signals, so it's not really a big deal. But just to get some good practice, try to minimize the amount you're viaing through. Okay, and these are all the pins, and these are test points, and you can just route to all the test points. Auto routing. So you might be wondering, shouldn't a computer know how to do this? If I give it the schematic, can it just route it for me? Yes, it can. If you define your rules really well, it could be okay. And if you're making kind of like a dumb little board like the one that we have here, that might work and it might be fine, and that could save you some time. I really suggest not doing that, especially if you have like complicated designs. and especially as you're learning, don't have auto route do things. It can do some really funky things, and you have to like dig into the rules and figure out what's going on, and sometimes it can be more hassle than it's worth. And for now, like just try not using auto routing. If you want to play around with it, you're more than welcome to. I'm happy that you do that. If you want to come to your design review for layout with an auto routed board, maybe I won't even notice. But really, when you're learning, just do it yourself for now, and maybe play around that later if you want. I just want to let you know it's a thing that you can look at. Ground planes. These are something that a lot of beginners don't do on their boards, which make them a little bit worse than if you know how to use them. So almost every component, like not every component, resistors, capacitors don't have ground, but every like IC is going to have ground. Everything, a lot of things can be connected to ground or power. And it gets kind of messy if you just try to connect them all. Like, see how this is like, a really long trace, first of all, and it's kind of messy, and routing through it will be difficult because now it's routed in every direction. It's much cleaner this is. There's a few other traces here that are ground. It's just a lot cleaner if you have a ground plane. So what a ground plane is you place a big layer over it, and you say everything that's connected to ground, connect to this layer. And everything that's not connected to ground, don't connect to that layer. And it will just connect all the grounds together to that plane. And I'll show you, it's better if you see an example of this. Basically, there's a hidden layer right here that's the ground layer. And I'll show you what that looks like and how to do it. But you can connect all your grounds there, and it just makes your routing a lot cleaner and easier. You can lay your ground plane over the entire board, and it will only connect to what you want it to connect to. It's smart like that. An important thing that this helps with is something called ground return loops. And this is a really, really, really important concept in PCB design and layout, is the return of your signal. So if you have a high-speed signal, it's going from, let's say, here to here, the ground path is going to want to return as closely under that path as possible because of inductance. So if you remember inductors or loops, taking like E&M, you want to create smaller loops for lower inductance. And if you have more inductance, you're going to be like filtering your design essentially. So you want to lower the inductance as much as possible by creating short return ground planes, return ground loops, which is you can do by creating a ground plane. If it's covering the whole board, it will have much more ability to go back and forth underneath that trace. For more information about this, you can check out Jeremy's guest lecture. It's on the website. He talks about this quite a bit and shows some like physical examples of these ground return loops, which are very important for good design. So yeah, placing a ground plane over your entire design will just make things easier for you, and it will make your design actually better. So it reduces, it just reduces your complexity and makes your board better. Double win. Do it. You can also, if you want, you can put like a ground plane on the bottom and a power plane on the top. That's going to like reduce the amount of like routing you have to do again. It's kind of harder to see on this bottom layer, but I did that same thing here, and just reducing the amount of traces that I have overall and the complexity of the board makes it a little nicer. So you can do one side power, one side ground, and then if you had a 4-layer board, what you would do is have one internal layer be ground and one internal layer be power, and that way you have your entire surface for routing traces and signals and stuff. So yeah, very important concept. Use these. I will show you how. Polygon port. So a polygon port is how you do a ground plane, but it also can be used for more local things. So you're gonna have your battery, and you're gonna have that connecting to the switch. And what you could do is, it's connected on both sides. You'll see when you place this. So what you could do is you could do something like this, where you place a big fat trace. Power line should be pretty thick, and you could do that, and you could go around like that. Or you could just place a polygon port, which is this block. And this is what I kind of had hidden from you guys. If you see, it's not a big. This whole thing isn't covered in red. It will be. You can just hide these, because I find them difficult to look at personally. But that's what this would be. It would be entirely covered in this red layer. And what this would do is it would smartly connect everything that needs to be connected to the trace that it should be connected to. So you can see that these are connected at all the points that they're supposed to be connected to, and they're not connected. There's a gap between them for all the paths that should not connected. And you can increase or decrease that gap in your rules. In layout, so you can change what that gap is. And there's also there's different ways of connecting these. This is just like fully connected, and it's the same copper. But what you can also do is something called thermal relief, and I can show you an example of that. But basically, it'd be like if this was connected to this power plane, it would be like trace here, trace here, trace here, trace here, instead of totally filling it in. And what that does is it provides thermal relief, which is basically like, let's say you're soldering this, and this is just basically just like a huge a plane of metal, so it'll just be absorbing that heat really easily. And if those of you who've had trouble soldering, you know, like if you can't heat something up, it's pretty difficult to solder it. So it would just be kind of absorbing all this heat. But if you have those little traces, it creates it just doesn't like sink as much heat as quickly, so it's easier to solder things. So there's some different options about how to connect your Polygon Ports. Yeah, it just smartly pours around things. Like you can see, just doesn't, these traces can just go right through it, and there's a gap on every side, so it's not connected to this plane. It's smart about it. You can also, there's also a function for like removing something called islands. So this right here, see it's not actually connected to anything. It's not actually connected to this plane. You can remove those islands, and it will just remove that copper, and there's no real reason to have that copper. So those Polygon Ports. Trace rules. You may be wondering, okay, if you can have traces of different thickness, how do I decide what thickness that should be? You can, if you have like really high power things, you can use something called a trace width calculator. A lot of like manufacturers, you just search like trace width calculator PCB. You come up with a calculator and it'll tell you, okay, how much current is going through this? What is the thickness of your layer? That kind of thing. And basically, what it's doing is just calculating the resistance of your trace and determining like how much resistance you can have to like not burn too much power and heat up the board too much and possibly burn out your traces. So higher current things. If you know like the equation for resistance, it's like it's dependent on like the length and the width and like the thickness, and then also like the resistivity of your material. So it's just basically calculating those things and telling you like how thick it should be to make sure that you can push enough current through it, because it is a resistor. You know, it's a metal, but it has some like finite resistance. So you're going to be burning power through those traces. So the thicker it is, the less power you're burning through it. Which is another reason why you should use power planes and ground planes, because they're basically just like really thick traces, and they can source a lot more current. So things not to do. Oh, I actually wrote the equation here. I didn't even see that. One thing not to do is don't change the size of the trace connecting 2 points. Like don't do this. Don't like make it thicker in the middle. And that's not actually useful. Like this is just creating like bottleneck points. Don't do that. This is not useful. Just keep it consistent along one trace. If you have inner layers, you have to use thicker traces for 2 reasons. One thing is that depending on your stack up, like check out the layer stack up, so you know how thick each layer is. Sometimes the inner layers are thinner. They're actually like just like a different thickness than the outer layers. So that's, again, you can plug that into your trace width calculator, but also just consider that when you're using internal layers, like if you have internal signal layers, which again you don't have in a 2-layer board, but let's say you did for like a 6-layer board or an 8-layer board. Those are often thinner, so you have to use thicker traces. Also, you have to consider that it's insulated by the dielectrics because it's basically sandwiched inside of this board. So it's covered in things. It's not on the outside, and so the heat, like the ability for heat to dissipate, is lower because it's insulated inside of the board. So just use thicker traces if you're going to be doing any internal routing, which again I don't think you'll be doing probably for this course, but just to consider as you move forward in your design education. Longer traces also need to be thicker. Again, that relates to this equation. You know, if you have like a longer length, you have a higher resistance, so it needs to be thicker so that the cross-sectional area is higher, and again, your resistance goes down, so you're not burning as much power through these traces. We'll talk about this a little more when we go to the advanced topics, but certain kinds of traces, like really high-speed things, like communication protocols and that kind of thing, have something called controlled impedance, where you need to basically like the resistance of those traces needs to be like really tightly defined so that it can communicate with these other high-speed devices. And again, we'll talk about that more later, but if you're considering using any kind of high-speed things on any of your final projects, like if you're going to be doing USB to charge, or to, well, I guess if you're charging it wouldn't, but if you were doing it to like program it via USB, or you wanted to connect something else via USB, you'll need to consider this, and we'll talk about that more a little later. But just keep in mind that it's going to be a little more complicated. And it's going to let me see my bottom note. Oh, yes. Do not route at right angles. This is something that's kind of archaic, honestly, in board design. It used to be because these could kind of peel up based on the way that the chemical etching that was done to create these boards. That's not really something that's done anymore, so it's not really as relevant. It is considered good practice, and when you get to really high speeds, it will matter. But just for now, don't have right angles on your boards. This is just good practice for if you ever move to higher speed things. And also if other board designers see that you have these kinds of things on your board, they're going to laugh at you. So just do it correctly, and everyone's happy. Vias. a few things about vias. So these are just different kinds of vias. This one, these are both vias. They're just holes to the other side, so that you can see these traces go, and then you can't see them anymore because they're on the other side. They're just viaing to the opposite side, the bottom side. A few different things about how you should do your vias. Don't put them on pads. So don't put a via on a pad. This is bad for manufacturing. Basically, what can happen is if you're getting this assembled by a fab house, solder paste, which is that stuff that's basically like solder, can wick into the via, so it can like kind of like flow into this via, and it won't leave as much solder paste on the pad. It will go into the hole, and it doesn't leave as much solder on the pad, so it won't make a good connection with the component that's placed on that pad. If you want, you can do this if you have a really tight design that needs to be really tiny and you have to put vias on pads for some reason. You can do this. It might not matter, especially if you're soldering yourself. It won't matter. But just as a general tip, try to like just place it like right outside. It's okay. This is not taking up that much more space. I would just place it out here. So on pad, not on pad. Good. Tenting vias. So what a tented via is you can see this is kind of exposed copper, and this is not exposed copper. You're not actually soldering anything to these vias. These vias literally just take a trace from the bottom to the top, and the only reason they're plated is so that it can like maintain that connection going to the bottom. You don't actually need to interact with these vias ever. So what you can do is you can tent them, and what that means is it will cover, it'll use this, see how this solder mask is covering this, and the solder mask is not covering this. It'll just tell you, cover the via with a solder mask, so that you can easily, so it's not like exposed copper. This can help prevent solder wicking. If you have like a via really close to a pad, it won't be as likely to wick into there because it's like covered, so it's not actually connected to metal. It's not gonna suck that solder down. If you don't cover the vias, you can use them as test points. So that's a pro for not tenting your vias. So there's pros and cons of tenting vias. I just always tent my vias. I'm just gonna make designated test points instead of using my vias as test points. But if you're really tight on space and you don't want to place like a separate test point, you can just throw a via on there that's not tented and use that as a test point because you can have solder something to this, connect to it, and read it on an oscilloscope or whatever, or multimeter. So pros and cons: tenting vias, not tenting vias. One really big thing with vias is try to make them consistent sizes. Let's say you have like a 10 millimeter hole and a 12 millimeter hole, or mils, 10 mils, 12 mils. It's going to be using a different drill bit to manufacture. So you have to drill that out, switch drill bits, drill that out, and that just costs more money. On the really small scale, it doesn't really matter. But if you're mass producing things, if you're getting something really like intense done and it's going to cost more money, keeping vias the same size will minimize the number of drill bit switching you need to do, which will minimize the cost of your board. So if you just keep them the same size, also it's just like, nicer to have things that are the same size and not like be kind of like wacky all over your board. So just keep them the same size. Determining the size of the vias you should have. The internal hole should be at least, like the diameter should be at least the width of your trace, so that you're not like creating like a little like pinch point for your current flow. And then it doesn't really matter, like the annular ring should just be like bigger than that, just like enough bigger. So we can go over some like common things. Usually it's like I'll do like a 10 mil internal diameter and a 12 mil external diameter, something like this. Yeah. Silkscreen. Again, this is the text, so it's written on the board. This is a board that I made with a bunch of different connectors, and they just had headers. If you just have these and you didn't have any text, it's like impossible to tell like which one's which. You have to like go back and check the schematic, and someone else who's using your board doesn't have a schematic, doesn't want to look at your schematics, doesn't want to do that. So just like label things. This is really important for ground. Like these are bidirectional, these are not keyed, they're not directional. So if you could like easily plug something in backwards and you could like, connect power to something that should not be connected to power, like ground, for instance. You could like short things and break things. So like label which one's ground. I put a little ground symbol just like on the layer that's ground, and then you can see that this is RX, this is TX. Designators. So again, designators are like telling you which what the component is. So this is like the 44th header, this is the 43rd header, the 41st header. This is a really big board that I made, so a lot of headers. But these are the designators that will tell you like what the component is. Make sure these are visible, because when you're actually like plugging things in, you're going to be looking at your BOM and you're going to be saying, okay, C1 is this capacitor. If you can't see where C1 is, then you don't know where to put it. And someone else assembling your board or making your board for you does not know where to put it. So make sure you can see these. Don't put them like under components. You can also, if you want to, put fun things on your boards. I will show you guys how to do this in Altium. You can put like pictures and poems and whatever else you want on there. It's a lot of fun to kind of play around with the Silkscreen. You can like personalize it and make it your own, and it's a lot of fun to get back a board and and see like something fun and customized on it that really makes it yours. So I'll show you how to do that. Things like designating like, you know, like which thing is which, LEDs, like if it's an indicator, like if you're like having an LED turn on when like power is good, label it power good and make that our LED green. Like just usability things for people. Just tell people what things are. If it's a switch, I didn't do this on the board that I gave you guys. I should have. I did not label which side of the switch was on and off, which is like just stupid. So when you make your boards, label which side is on and which side is off, because then you can actually like not have to like plug the battery and have it start playing. You plug the battery in when it's off and then turn it on. Sorry about that. I did not do that. Shame on me. But you will do it. You will be better than me. Design rules. So I've been talking about rules a little bit. Basically, you can just set like how you want the board to operate. So you can like set all these rules of like how Altium will like, or whatever design software you're using will like operate. So you can say like, okay, like how close can I get? How close can I put a trace to a via, or a trace to another trace, or a trace to a power plane? How thin can my traces be? This is relevant to like what your manufacturing capabilities are. Like, can your manufacturer make a trace that's 2 mils? Probably not. So what's their min width? 10 mils is usually a good bet. If someone can't do 10 mils, they're not a good manufacturer. Use someone else. And then also max width, like what's the maximum size I can make a trace? That's less relevant to manufacturing, more relevant to like what you want your board to just be. How small can you make your holes? Again, minimum 1 mil? Probably not. You're probably not getting 1 mil drills, so probably don't use that. A design rule check is something you can just run in your board. It's kind of like the verifying with schematic, where you can it'll just check to make sure that your board is following all the rules. If not, it will give you errors like, you put your traces too close together, or this hole is too small. And so run that frequently, and it'll just tell you if you're screwing up in any new exciting ways that you're not aware of. So just a few other quick things. I'm almost done. Clock line symmetry. So this is these are high-speed signals. So making sure that these lines are like roughly symmetric and not different lengths is really important, because then this is basically a clock signal. So if these are different lengths, significantly different lengths, they'll travel at different speeds, or not different speeds. They're traveling the same speed, but they'll travel different distances, which means that they will get there at different times. So if you want good timing, just try to make your clocks symmetric. At this distance and with these speeds, probably not going to make or break your board, but it's good practice when you have a lot higher speed signals. So just do it, and it'll like make you a better designer. So don't do this. Do this. Make them symmetric. Make them roughly the same length. Make sure all of your headers have room. So if you have a header being plugged in, make sure that there's space for both the header and whatever is being plugged into the header, especially if that's like a female part. It can also often be bigger than the male part, so just make sure there's space for that to be plugged in. Switch between 2D and 3D frequently to like look at what your board's actually going to look like, and make sure you're not getting CAD goggles. One of the things I did when I was first making this board was I put, or actually the ref I gave you guys, if you'll remember, I put the battery connector like right below the switch, so you can't actually plug the battery in unless you make the battery connector backwards. Maybe do that better on your board. Maybe don't put that right next to each other, so that you don't have to worry about which direction you soldered in. It'll just work. Things like that. So just look at it in 3D and be like, okay, how am I going to interact with this board? Does this make sense? Let's take a look. So, okay, that's just like a brief introduction to PCB design, to layout. All really important things to think about. So I'm gonna go now and like actually show you how to do some of these things in Altium, like how do you import these parts, how do you connect them, what buttons do you press, etc. But these are the things you should be thinking about when you're making your design. This is from the clock tower PCB. Your board will be different than mine, because I had this header that's like a programming header essentially, and you're not going to have that. So you cannot just copy this. Yeah, we'll have design reviews and we'll talk about it.